And let me just jump over to mail to make sure that nobody well, okay. Well, all right. So I'm a little puzzled here as to what has my starting of this thing has been a minute or so late and a little bit confused. I was so absorbed in what I was doing. Let me say, first of all, that I took a second look at that problem that was the problem of the magnetic field generated by a current loop, and I made some corrections in the online notes. These are the notes of, I think they're called the notes of 25 October, although it wasn't simply October, it was partly, I mean, they started on the 25th of October and then went on. So you remember when I was doing that one in class, I was following a treatment that was actually erroneous, and so I had to stop in the middle and just drop it completely. So I corrected that error, and so if you look at that iPad transcript now, you can find that it's reasonable. So I think I'm going to get rid of some of this stuff on it's just wasted iPad space. So I'm going to switch now, and so I can do examples here. Now, the ideal thing is for students to ask questions either on the chat screen or just by talking. And if there isn't any talking or nothing on the chat screen, then I'll just review some of the GR that we were going through. So the essential idea is to use tensors, and tensors are quantities that transform simply under changes of coordinates. And by changes of coordinates, we mean the change should be 1-to-1, and it should be smooth so we can differentiate and so forth. So the idea is that we have x prime I of x and is smooth and 1-to-1. And so it's invertible. So xk, say, is a function of the x prime, and that's also smooth and 1-to-1. So that's the idea. We have nice transformations. We're not going to deal with singular transformations, at least not in this course. The simplest tensor is a scalar, one that just doesn't, s prime of x prime is just s of x. This parenthesis x prime means in the new coordinates, and the s prime means the new tensor in the new coordinates. So a scalar is one that just is a function, a scalar field is a physical quantity that's a function of the coordinates, but doesn't change the coordinates. The next simplest, of course, is a vector, and there are two kinds, covariant and contravariant. The covariant ones are just like derivatives of a scalar. And so in the primed coordinate system, the ith component of the covariant vector at x prime, it's the derivative of the scalar at x prime, but s prime of x prime is s of x, so we just have this derivative. The chain rule tells us that that derivative is this linear combination where we sum over k, and this derivative, on the other hand, is what we were calling the vk. So a covariant derivative, a covariant vector is one that transforms simply, which is to say, it transforms this way, it transforms like a derivative. And any quantity that transforms this way is said to be a covariant vector. Contravariant vector, on the other hand, is one that transforms like the differentials of a coordinate, and dx prime I is just the chain rule formula, partial of x prime I with respect to xk dxk. So I don't see any questions in the chat, but go ahead and type one in or shout it out. So far we've talked about tensors of rank 0, tensors of rank 1. The tensors of higher rank transform like products of vectors. And so, for example, if you had 3 vectors, 2 covariant, 1 contravariant, that's a tensor of rank 3, and it transforms just the way a product, it has to transform this way. So in other words, if we had an arbitrary tensor, any tensor, every tensor, so let me in fact go back to this and go to say red. So a tensor T, and in this case it would be ijk prime would transform just this way. And in other words, it would be partial xl, partial x prime I, partial xm, partial x prime j, partial x prime k, partial xn times t, and n, instead of ij, we have lm. So it would look like that. And of course, we'd be summed, and it would be a sum over L, M, N equals 0 to 3. One example is the Kronecker delta, which is a mixed second rank tensor because it has one upper index, one lower index. It transforms this way. But the delta, the Kronecker K, delta Kj tells you that the K is the same as the J, so the thing looks like this. We're summing this just by the chain rule is the partial derivative of x prime I with respect to x prime L. That's just the Kronecker delta. And of course, the Kronecker delta is 1 if I is L and 0 otherwise. So this Kronecker delta is invariant under changes of coordinates or under general coordinate transformations. And so the basic thing is then that tensor equations don't change when we change coordinates. I mean, at least if we make sensible changes of coordinates. They're the same in all coordinate systems. And so a theory written in terms of tensors has equations that are true in all coordinate systems if they're true in any coordinate system. Another reason why you want to use tensors is that if you don't use tensors, then you are building into the physics or building into the theory the coordinate system that you're using, because you're writing equations that aren't tensor equations, and so they're true only in a specific coordinate system. Well, it could be that the specific coordinate system is one that, how shall I say, it's one that somehow conflicts with the nature, or conflicts with nature. And for example, let's give an example of a coordinate system that conflicts with nature. Suppose we said that we were going to do cosmology in which we had we just used special relativity. So we would have a space-time that would have, if I switch to green, say, it would have one time and 3 space dimensions, and they'd all 4 dimensions would be orthogonal to each other, and there'd only be 4 of them, and that's a coordinate system that's inconsistent with reality, at least to the extent that space is our space-time is curved. Now, what's clear from general relativity is that space-time is curved, in that we live in a curved space-time that's embedded in a flat space-time of higher dimension, just as the surface of a sphere is embedded in a flat 3-dimensional Euclidean space. The term semi-Euclidean, by the way, just means that you have time dimensions in there. So some of the dimensions are time dimensions. And the metric of special relativity is -1, 1, 1, 1. And it's possible that that is the right metric for cosmology, apart from the expansion of space. But the other ones, well, suppose we were designing furniture, then we would want to have a metric zeta that would just be just describe space, flat 3-dimensional space. If we're using tensor equations to describe the shape of a piece of furniture, or the shape of an animal, or whatever shape of a building. On the other hand, our actual universe, the simplest cosmologies are the ones that are associated with the names Robinson and Walker. And in these cosmologies view our 4-dimensional space-time as embedded, our curved 4-dimensional space-time as embedded in a flat 5-dimensional space-time. And the space-time has an internal metric that's -1, -1, 1, 1, 1, if the universe is open, and on the other hand, -1, 1, 1, 1, 1, if the universe is closed. And so that's just to illustrate what this, so the idea then is we have a curved space-time. Curved means that it looks curved if you look at it from this flat embedding space. We, on the other hand, are stuck in our 4-dimensional space-time, and so it's harder for us to imagine that it's curved, but it's curved at least on small scales. Whether it's to what extent it's curved on large scales, so that the metric is that of there are 3 Robinson-Walker cosmologies, I should say. The third one, of course, is just that zeta is equal to eta. In other words, it's just the cosmology of special relativity, with the exception of the fact that the universe has a scale factor, so space is expanding. Anyway, the utility of these tensor equations is that the equations look the same if you change coordinates. So here, these are Einstein's equations, where this is the Ricci tensor, this is the metric tensor, this is a scalar. These are just numbers, and this is the energy momentum tensor. If we change coordinates, then the whole equation looks like this, and it's just that each of these things is given by how a covariant second rank 2 tensor transforms, and this is the way it transforms. And so here is, for example, a prime index L has to stay downstairs, and the prime index M stays downstairs, and the other indices go upstairs. And being upstairs, then they form invariants with the things that they match in the Einstein equation. Now, there are 2 or 3 big ideas that I'm going to go over today, which is just be repeating what I said on Tuesday largely. The basic metric, or the basic invariant of general relativity, is the squared separation between 2 points whose coordinates differ by an infinitesimal differential dxi. And the second rank covariant tensor, GIK, is the metric tensor. This is said to be the metric of spacetime. And as I said, it's sometimes useful to imagine that our 4-dimensional curved spacetime is embedded in a flat spacetime. Points then are labeled by our 4 coordinates. These points are physical points, and so they don't change when we change our coordinates. So they're scalars. And the change in the points when we change our coordinates, not when we change our coordinate systems, but at different points, the separation between a point at x and a point labeled x and a point labeled x plus dx is this given by this sum of the partial derivatives with respect to each of the 4 coordinates times the change in each coordinate. And this coefficient here then is a covariant vector, this being a contravariant vector and this being a scalar. And so we can think of our points as being points of the physical space as lying on a surface in a flat, higher dimensional spacetime. The basis vectors EI, these things here, are tangent to the surface, and they're called tangent vectors. And the inner product of 2 tangent vectors is the metric tensor of the physical space. And so what is since the embedding space is simple, it's just Euclidean space, or what's called Minkowski space, which is this space over here, which is Minkowski space, or if it's a Robinson-Walker space-time that's open, it looks like this, or closed looks like that. Of course, when I say here, what I did here was I left out the word diagonal. So in other words, what I really meant was that the open zeta is -1, -1, 1, 1, 1, with zeros everywhere else, and zeta closed is -1, 1, 1, 1, 1, with zeros everywhere else. So and so what I forgot to include here is this word diag. So zeta equal diag of this means it's a diagonal matrix in which -1, -1, 1, 1, 1 are the entries on the main diagonal, and this one also is diag. So I should have said diag when I described that. So in general, it's a diagonal matrix that is, I should have said that it's 0 when alpha is not equal to beta. And let me see if I can fix that on the fly. So let me try. So I've changed the LaTeX file, and unfortunately it's such a long file, it takes a while for tech to recompile it. So 0 when alpha is not equal to beta. And this is said to be the semi-Euclidean, means you have some minus signs. So there are some of these dimensions are time dimensions, in other words. By the way, it might be fun, and it is fun actually, to think about a space-time in which you have two time dimensions. That really, I'm not going to digress on it now, but you could think about it. And I've sometimes wondered whether the existence of quantum mechanics is because there are two time dimensions and we just haven't noticed it yet. But that may be totally silly, and I don't want to waste class time talking about it. So again, it's natural to think of a sphere as being embedded in flat three-dimensional space. In that case, zeta is diag 1, 1, 1. And the Robinson-Walker cases are diag -1, 1, 1, 1, 1 for the closed case, and diag -1, -1, 1, 1, 1. So that's two time dimensions in the open case. And as I said, that's pretty amazing. But the squared separation is the dot product of the change in the physical points of the 2 points in our curved space-time. And that is this inner product, and that's this metric of space-time. And this inner product here is the inner product with this metric zeta, which is diagonal. And we're always writing partial derivatives in general relativity, and so the idea of having a better notation is useful. And so the notation is S comma I is meant to be the partial derivative with respect to SI. It looks like this. Or if you have a tensor and you're taking the derivative with respect to I and K, then that is written this way. Semicolons are used to represent covariant derivatives. Well, we haven't gotten to covariant derivatives yet, but just so you know, a covariant derivative is a derivative that transforms like a covariant vector. So in this more compact notation, you can say that the basic invariant of general relativity is p comma I dxi dotted into p comma k dxk, and that's ei, that's a dot product of the tangent vectors multiplied by the dx's, and that's this metric of space-time times dxi dxk. And derivatives with respect to prime coordinates like this, you write that in common notation with comma, and you put the prime on the index. Now, I've been going on about embedding in a semi-Euclidean flat space-time because I think it's easier to think that way. Some people do general relativity without ever mentioning embedding, and you know, that's fine. It's perfectly all right to discuss general relativity simply in terms of the metric of space-time. and G, I, K, and forget about embedding our space-time in some flat higher dimensional space-time. I went over the quotient theorem before. Let me just this time just state it. So suppose B has unknown transformation properties, but its product with all tensors A of a given rank and kind is a tensor, then it follows that B must be a tensor. And the example I went through was that suppose B, when B is contracted with any vector A, you get a scalar. So then, or you get a scalar in all coordinate systems. And so B prime I, A prime I is BJ, AJ. Well, then you can show that B prime K is related to BJ by the formula that, by a formula that says that B is a covariant vector. And this quotient rule works in general. And it's very useful. Well, anyway, it's very useful. Now, the metric is a non-singular matrix. And the reason it's a non-singular matrix is that this squared separation between points whose coordinates differ cannot be zero. So in particular, GIK, DXK can't vanish unless all the DXKs are zero. But that means that the rows of G, now the rows of G, or am I talking the columns of G? Anyway, it means that G is non-singular. Right, these would, I'm confused whether I'm talking about the rows and columns being linearly independent. In any event, a matrix has a non-zero determinant if this can't vanish unless all the dx's are zero. And since G is non-singular, then it has an inverse, and that inverse metric is something we write as G upper IK. And we mean that it's an inverse in the sense that G inverse G is I, and GIK, GKL gives you delta IL in all coordinate systems. And so this inverse metric, you can apply the quotient theorem and say, well, since it satisfies this equation, and we know this is a covariant rank 2 tensor, this has to be a contravariant rank 2 tensor by the quotient theorem. Or you can go through it, the derivation in detail here. And what we do then is we know that if we take this inverse metric and sum it, multiply it by a covariant vector and sum, well, this thing is going to be a contravariant vector. And we then say that it is the contravariant vector associated with the covariant vector A. And similarly, if you have a contravariant vector A, upper I, the covariant vector associated with it is GKI, AI. So these operations are called raising and lowering an index, and they apply to all tensors. And for example, if you have a rank 3 covariant tensor, the corresponding rank 3 contravariant tensor is given by the product of T with 3 inverse metrics. The the tangent vectors are covariant, and if you multiply them by this rank 2 contravariant tensor, you get a contravariant vector. And these things are called cotangent vectors or tangent covectors. And their dot product with each other are, well, they're orthonormal. That is to say, the tangent vectors are orthonormal to the cotangent vectors. And the reason is that the cotangent vector, E upper I, is G upper I K E K, and that's dotted into EL. But the EK dot EL is GKL, and this sum is, since G upper IK is the inverse matrix, the product of these two matrices gives you the diagonal matrix in four-dimensional space, the four-dimensional unit matrix, and consequently, we can say that E upper I dot E lower L is 0 if I is not equal to L, and it's 1 if I is equal to L. We can also say that the lower tangent vector is a sum on of the metric tensor on the cotangent vectors, and again, it's because the cotangent vectors are given this way, and the G lower times G upper is the identity matrix, and you get AK. Well, and then you can show that the inner product of two cotangent vectors, well, it is of this form, and on the other hand, this with that is a Kronecker delta, and so that gives us GIL. So there we have all the relations. The dot product in the embedding with the embedding metric of two cotangent vectors is the inverse of the metric tensor of spacetime, and the dot product of two tangent vectors is the metric of spacetime. And now to go to covariant derivatives again. The basic idea is that a covariant derivative is a derivative that transforms like a tensor. And if you're differentiating a scalar, you automatically get a tensor in the sense of a rank 1 covariant tensor. But if you're differentiating a contravariant vector, VK, you're not going to get a tensor. And so how do you fix that? Well, you first make a scalar. And the way you make a scalar is you take a linear combination of the components of the contravariant vector with the covariant tangent vectors, and that then is a scalar. And you differentiate that with respect to XL, and now you have a tensor or a rank 1 tensor covariant vector. And since V is this linear combination, you differentiate both V and you differentiate the tangent vector. But when you've done that, you end up with something that's actually a vector in the embedding space. And you don't want to stay in the embedding space. You want to get back to Earth into our physical space. And so what you do is you take a dot product of this expression with a cotangent vector. And so you have the dot product of the cotangent vector with this structure here, which is this. And we've already seen that the EKs are orthogonal to the EIs, so that's delta KI. And then we have this new thing, though, that's the dot product of the kth cotangent vector with the nth derivative of the ith tangent vector, and that's this thing. And summing over I from 0 to 3, we replace I with a K. And so we have the nth derivative of VK plus VI summed from 0 to 3 and multiplied by the inner product of the kth cotangent vector with the nth derivative of the ith tangent vector. Well, that is a structure that has traditionally been called a Christoffel symbol of the second kind or an affine connection. It's written as gamma with one upper index, namely this one, and two lower indices, that. Now, let me just mention that since E lower I is the partial of P with respect to xi, EI, what is it? EI comma L is partial of EI partial XL. So this is the second partial of P with respect to XI with respect to XL. But partial derivatives commute. So this is also the second partial derivative with respect to XL with respect to XI of this. And that then is E sub L comma I. So we have that, switching to this, we have that this thing is equal to that. And that means then that gamma K IL is equal to gamma K Li. And so there are versions of general relativity that are said to be extended general relativity. My offhand feeling is that these are kind of crazy theories because I've derived this symmetry here from very basic, simple ideas, and I don't see how one can get away from it. But, you know, who knows? This notation, sometimes it's written as capital D sub L, sometimes it's written as a semicolon. So V upper K semicolon L, it's the same thing as DL of VK. And it's V comma L plus this linear combination here, or as it's traditionally written, VKL plus this affine connection or this Christoffel symbol of the second kind times VI. And so that's the way it looks. I'm just wondering if there's a mnemonic. Well, it of course doesn't really matter. What you know is you're going to have the Lth derivative of VK. Since VK has an upper K, you know that the Christoffel symbol has to have an upper K. And you know that you're going to have a linear combination of the V's. So you have to have a V upper I. And then you have two leftover indices, I and L. So they've got to go here. And it doesn't matter whether it's IL or LI because the Christoffel symbol, as I said just a moment ago, it's symmetric in its lower indices, so it really doesn't matter. Oh, hell, I just ran out of the notes that, I blew away the chat. I'm sorry, I didn't mean to blow away chat, so let me bring chat back. I thought chat was something else. Let me grab the book version of this now and go back to, okay, so we've just done covariant derivatives of contravariant vectors. The question is, what about covariant derivatives of, well, for example, cotangent vectors? We know that the derivative of the Kronecker delta obviously vanishes, and consequently we get this relation, which is actually quite important. This is used many times. The dot product of the kth cotangent vector with the ith tangent vector, the Lth derivative of it is, well, the Lth derivative of the kth cotangent vector dotted into the ith tangent vector plus the dot product of the kth cotangent vector dotted into the Lth derivative of the ith tangent vector. And so if we take the covariant derivative of the kth cotangent vector, what we get is its derivative and then this Christoffel symbol. But on the other hand, this Christoffel symbol, if we use this expression, we can rewrite it like this. On the other hand, this product here, this is an outer product of E lower I with E upper I. This is the identity matrix. And so this turns out to be EKL minus EK lower L, and so it vanishes. So this is just a statement that this is a proof that the covariant derivatives of the cotangent vectors vanish. What I think, well, let's just use this. Tomorrow, maybe I will say a little more about this because I should have developed this a little more thoroughly. So let's skip this for a second and go to the covariant derivatives of covariant vectors. So here we do the same thing. We have here a covariant vector bk. We need a scalar, so we take its dot product. We take as a linear combination of the covariant the components of the covariant vectors times the cotangent vectors. That's a scalar, and so its derivative is a covariant vector. And when we differentiate the v's and the cotangent vectors. And then to get something that's just in our space-time and doesn't refer to these vectors in the embedding space, we take the dot product with a tangent vector, the ith tangent vector. And the ith tangent vector then hits this kth cotangent vector to which it's orthonormal, and so we get a Kronecker delta, and we're left over with this thing. And so what we have then is the elf derivative of the ith component of the covariant vector and vi, and then using that identity that I derived earlier, this thing is minus EI comma L dot EK, but that is the Christoffel symbol of the second kind. And so what we have then is that the covariant derivative of a covariant vector is the ordinary derivative minus a linear combination of Christoffel symbols times the components of the covariant vector. Okay, now, how do you remember how to do this? Well, obviously, you're going to have the elf derivative of the ith component to give you this. And then you have to remember that there's a minus sign. And then you have a Christoffel symbol. Okay. Well, you know that I and L are both lower indexes, and so they have to go here. And it can be IL or LI, it doesn't matter because it's symmetric. There's one remaining place to put indices, the indices that we sum over, and that's the index K we sum over. And so we put gamma K, VK. So that's how we construct a covariant derivative of a covariant vector. And this is then, this covariant derivative of a covariant vector is a rank 2 covariant tensor. You can think of it is that way because it's the inner product of a covariant tangent vector with the derivative of a scalar, which is a covariant vector. So this is a rank 2 covariant tensor. And then once again, I mentioned that this, when you're making the covariant derivative of a covariant vector, you have a minus sign in front of the Christoffel symbol. If you're taking the covariant derivative of a contravariant vector, no minus sign in front of the Christoffel symbol. And if you have covariant derivatives of tangent vectors, well, once again, you have, just by definition, it would be of this form, using this expression here, with VI being just EI, you'd get this. And now this structure here is the identity matrix. And I guess I should try to say why it is here. I skipped in the derivation or in the discussion tonight, and I've been rewriting the notes, the class notes, and I skipped this part of the class notes. Maybe the best thing to do is to drop back to the trouble is I can't find it immediately. So the point is that E lower k, is the four-dimensional identity matrix. And the idea here is then that these EKs are vectors that look like this, and these are vectors that look like that, and it's the outer product of these two vectors. I think we need a notation for outer product of vectors. You see, I just wrote the EK next to the EK, and that's kind of confusing. And so there's a need for a better notation here. Unfortunately, Dirac passed away 20 years ago or so, and so we can't ask him. Why is this the identity? Well, EK summed, dotted into, say, EL, well, this is going to be EK delta LK, so this is EL. So that's what we expect of an identity matrix. That is to say that this thing is an identity matrix in the sense that if we dot it into EL, we get EL. And on the other hand, if we take, say, EI and dot it into EK, well, EI dotted into E upper K, that is delta KI EK, and so that is E lower I. So what we see here then is that this quantity here and this quantity here, when dotted into EL on the right, gives you EL. When dotted into EI on the left, gives you EI. So EK, the outer product of these, of the cotangent, the kth cotangent vector with kth tangent vector, summed over K from 0 to 3, if we're talking about general relativity, this is the 4x4 identity matrix, which is 1, 1, 1, 1, zeros everywhere else. Okay, so we're a little over time. I don't see any. Oh, here. Okay, so there's a question from one of the students. Could I please update the class notes file? Well, I meant 13.1 and 13.3 in the book. So it's the ones in the book. That's why, that's what it is. It's not. So let me switch over here. Whoops! Oh my gosh! All right, hold on. in fact, I can in fact show you these problems in real time. If I just go down here to exercises. So there they are, 13.1 and 13.3. They're right here, and they're in the book there. And so since, oh wait, I need to have this in the right screen. So here are the exercises, the problems 13.1 and 13.3, and this is all being recorded, and so at least I hope this is the screen that's being recorded. So I'm going to stop now, and you'll be able to read it on YouTube if you don't have a copy of the book. All right, so I'm going to stop